So in this module, so far we have discussed about the signal transmission through LTI systems. Under these signals, we have discussed about energy signals and periodic signals. Now, today we are going to discuss about the random signals, because the random signals are also called as power signals. Power signals comprises two categories. One is periodic signals and random signals. Okay. So in this class, I'm going to introduce you the fundamentals of random signals. Then in the coming sessions, I will be discussing about the random signal transmission through LTI systems. So let us see what is random process, because random signal is a child of random process. So basically random process is like a mother and random signal is one of its childs. Okay, one of its children, sorry. So this is a random process, basically a parent process, capital X, as a function of time and space. Generally we say time and space. So time and space variables. It represents a family or ensemble of time functions where t and s are variables. Basically s is a ensemble variable. We don't physically, as in case of image processing, images or pictures, we don't have any spatial variable here, but it is some variable other than the time variable. Okay. So here I will read it again. A random process x of t comma s represents a family or ensemble of time functions where t and s are variables. Okay. Each member time function is called a sample function or realization of the random process. So for example, you have here, I have shown one random signal here. So if I take this signal, first signal, on vertical axis, I have voltage or current, something like that, some quantity, dependent quantity, which is based on the time. As time progresses, this parameter, voltage or current, changes in this way, randomly in this case. So this is called time function, because it's a function of time. Similarly, I take another one, time function like this, and basically it is a time series. It is like a time series, and but continuous values are continuous. And here it is again another time series, and we have, because it is a continuous signal, probably I should say time signal, not so, we don't say time sequence kind of thing. So time signal, and this is another time signal. I will take so many number of time signals. Okay. So this a set of time signals I will take. So this total thing, I can call it as a random process. So horizontally there is a time variable, vertically there is variable s here. S means here probably you can consider this kind of suffix as s. So this is, if s equal to 0, this is s equal to 1, s equal to 2. So I can say that it is the set number, the time function serial number, I should say. Okay. It is not really space. So, but, I mean, is equivalent in that way. Okay. So these are all set of time functions, is called random process. So this is the total family of random process, which contains several, means infinite, basically infinite set of functions. And what is the length of each function? Each function is also infinite. That is, t is between minus infinite to plus infinite. Okay. Similarly here, if I take center one as x nth waveform, This is n plus first, n plus second waveform. This is the previous waveforms, n minus 1, n minus 2 in the set. Okay, so all this is called as the random process. Now, and stationary random process. So stationary random process means, what is stationary? Something is stationary. Something is not changing in the random process. Okay, what is that? It is the statistically parameter. Okay, statistical parameters, you can say mean and variance kind of thing, you can say, or you can say first order density function or second order density function, that is joint density function, third order, fourth order, nth order, like that, density function and joint density functions. So all these things put together, they characterize random process. Okay, they characterize not only random process, even random variable. When we say here, each time function, I can consider it as it is a time function, but there is a variable also involved there. So in that way, I will just go back and see here, when I take at this point, at t equal to t1, this is the value of this, at this instant, this is the value of this time function, and at t equal to 0, another time function is there. So this is what you have the value in the second one, the third one here, this is the value, in the fourth one, this is the value. So these are all random variables. Okay, I should say that this is this and this and this. Vertically, when I sample this one, the values I get, I can call it as a random variable. So this is a time function. Vertically, it is a random variable. So basically, random process is a set of time functions or set of random variables. Okay, vertically, infinite vertical lines I can draw like this. I have infinite number of random variables in a random process, and horizontally, if I take infinite number of time functions in the random process. Okay, so that is how it goes. Now, let us come to stationary. Now, here everything is random. So the success of a mathematician or scientist lies in the capturing of the random process. Okay, knowing, characterizing the random process, because everything is random there. So something, some feature of the random process, some characteristics of the random signal or random variable or random process, we have to capture. So that is the successfully done by mathematicians and scientists in the form of ensemble averages, in the form of density functions. Basically, it is a density function. So first order density function, if I take, I can say that what is first order density function? If I take a variable like this, let us say this is the density function, this is x, and this is f of x. So this is f is nothing but probability density function. So this is what is. So basically, this is the random variable which takes values from 0 to towards minus and towards minus. Also, sometimes there may not be minus, always positive or only one-sided. Okay, so that means the random signal is maybe bipolar or unipolar. So in this case, it is a bipolar signal. Horizontal represents the range of the random variable. It takes range of the random values it will take, and how many times each one is occurring. That is what is the, theoretically, if we infinite bins, if I decide, divide, I will get a continuous curve here. So this is nothing but first order density function. Okay, so that is what I have shown here. F of x1, t1. Why t1 I have added is this random variable, whatever I am putting here, it is nothing but x of t1. That is at instant t, I have taken one random variable on the horizontal axis, and its frequency, how many times each value is occurring, I am drawing as a curve. Okay, because as the bin width, if I take infinite values on the x-axis, I will get a smooth curve. Okay, so that is what is first order density function here. And similarly, I will take another random variable from the random process at t equal to t1 plus tau. That means tau seconds away from the t1. Okay, so here when I go back here, so this is what you have. At T1, I have this random variable vertically, and at T2, I have random variable vertically. And the difference, the time difference between these two can be tau. So in that case, T2 equal to, in this case, T2 equal to T1 plus tau. Okay, that is the scenario I am showing here. So here, I have taken two random variables, one at T1 and another one at T1 plus tau. Let us say T1 plus tau also I have the same kind of thing, approximately. Okay, this is, both are same at T equal to T1, at T equal to T1 plus tau at both vertical slices. If I take both variables, they have the same first order density function. So that is for any T1 and any tau. So what it means is, I can move this T1 towards left or towards right continuously anywhere between minus infinite to plus infinite. I can modify this T, I can shift this vertical line, and similar way T2 also I can shift anyway. So in that sense, if for a given T1, tau also can be changed. Tau can be increased or decreased from T1. So in that way, the T and this T1 and tau both are random variables. They are any values. They can take any value. So for all values within because they are horizontally infinite, vertically also infinite number of sample functions are there. Okay, and sample functions means time functions. So both are there. So I can, these two parameters span minus infinite to plus infinite. And so this is the first order. What is this one? So irrespective of the time, that means the density function, first order density function of any vertical slice in the random process follows the same shape, irrespective of this T1 and tau. So it is independent of time. You may take random variable here in the process or somewhere here, both have the same, anywhere you take. So then it is the global property. Earlier it was the local property at T1, and this was the local property at T1 plus tau. Now these local properties are common everywhere, so it has become a global property. So a random process is called stationary to order 1 if its first order density function does not change with a shift in the time origin. Okay, so you can shift to any time origin. If I take, it should be same, independent of time. That is what is the meaning of this one. Okay, so that's why it is stationary. The density function is stationary. Density function is not changing with respect to time. The waveform may change. For example, here, if I take these values, set of values are different, totally different from the set of values of this. They are random. This is a set of random values, set of random values. So this is one random variable, another random variable. But both have the, even though instantaneous values, I mean, instantaneous values means individual values. They are different. Their density functions, they are same. Okay. So that is what is called first order stationary random process. So the mean of the first order stationary process x of t itself is a random variable. Okay. So what you can find is here, for example, let us take this variable. Find average value of this, mean value of all these values, then mean value of all these values. So like that, you take this mean value, you take, it has some value, and this mean value is also same. This all mean values are same vertically. So what it means, I am taking the expectation operation. Expectation it is called, because I am not taking average along time axis, correct? So I am not taking average of this waveform. I am taking individual samples at time instant. At certain time instant, I am taking individual values from each time function. Then I am taking mean value. So this is called ensemble average. If I take horizontally, each waveform wise, this is time average, another time average, another time average. Like that, I have several time averages here. Here, several ensemble averages here. These are vertically, if I take average, they are ensemble averages. Okay. So that ensemble average is represented by the expectation value like this. Okay. So this is one vertical, then it can be T1, T2, T3 like that. And this quantity is nothing but mean value of all vertically taken values. That is random variable at T equal to T1, T2, T3 like that. So for that, if I take expectation, I call it as X bar. It is represented by X bar and it is a constant. Okay. So the first order process means whose expectation of the random variable taken at any instant is constant. If the mean is constant or ensemble average, it is ensemble average is constant, then it is called the first order stationary random process. Okay. So that is what all about first order stationary process. Now let us move to second order stationary random process. So in this case, what I have taken x1 and x2. x1 is from T1, x2 is from T2. That means at T1 I have one vertical slice, at T2 I have another vertical slice. This vertical slice I am calling as x1, another vertical slice I am calling as x2. So earlier separately I have taken, now jointly I am taking the density function of these two, joint density function. That is second order density function I am taking here. Okay. So this is, how I can explain to you is, for example, I have one set here T1, T2. I will take probably another set here. I will take another set here. And this is pair. Here I have taken T1, T2 one pair. Here I will take another pair, that is T3, T4. T3, at T3 and T4, I will take another pair. So this is the pair. So if I find the joint density function of these two is same as the joint density function of these two. Okay. Joint density function of x T1, T2, I will just loosely call it as x T1, T2 is same as the joint density function of x T3, T4. Okay. So that is what, here one pair joint density function, here another pair joint density function, these two are same. Then in that case, I call it as a second order stationary. That means the second order, a random process is called stationary to order 2. Stationary to second order, I should say, if its the second order density function does not change with a shift in the time origin. Okay. First x1, x3 I have taken here. What is the shift here? Both I am taking this side. This is the shift. Okay. Not the difference between these two. Okay. Here T1 plus tau. Here T3 plus tau. Okay. Like that. So, but this difference is same for, okay. This is tau difference. Here also tau difference. So this set shifted to this one. This is the shift here. So that is the shift. See, if you see here, T1 is shifted by tau and T2 is also shifted by tau. So this T1, T tau, I can call it as per my diagram, I called it here as T3 and I called it T2 plus tau as T4. Okay. So this is what I have. Now, I already explained. So if the second order joint function is same irrespective of the shift, it is not dependent on the time shift, then it is called a second order stationary process. Okay. Second order stationary random process. Now, what is its property? Because the moment you take joint density, you can define the autocorrelation function. Autocorrelation function of two random variables. One is xt1, other one is xt2. These are the two random variables. So I am taking the correlation between these two random variables. Okay. Now this is between T2 and T1, and that I am replacing with T1 equal to T and T2 equal to T plus tau. Okay. So the difference is tau. Now this is This is how I define. That means this autocorrelation function will remain same. Okay. So a second order stationary process has autocorrelation function given by this expression. Why I am using here? Because after multiplying these two processes, you are taking ensemble average, because they are averages for ensembles. This multiplied by this multiplied by this. All these things are products basically. Again, you are adding vertically. So that's why it is ensemble average, and is a function. This autocorrelation function is a function of time difference T2 minus T1 only. This is the T2, T1, T2. Tau is one value. Then again go to another. So another tau means keep T1 here, shift the T2. Another tau. Increase the tau again, increase the tau, like that for different values of taus I do. And in the same way, this side, left side, minus tau, like this you go on increasing. So that is what is tau parameter. And actually this tau parameter is again theoretically, what is the tau? It can take, tau is minus infinite to plus infinite. Okay. So waveforms T1, T2s are between minus infinite to plus infinite. Tau is also between minus infinite to plus infinite. So a second order stationary process is also a first order stationary process. That means if the autocorrelation function does not change with time shift, the mean value also won't shift. Okay, so that means if the second order stationary process, if the process is second order stationary, it is also a first order stationary. Okay, that is the important point. Another thing, the random process which is both first and second order stationary is called wide sense stationary process. Okay, so because anyway second order, once the second order is satisfied, second order stationarity is satisfied, first order stationarity is also satisfied. And here if both are satisfied, then that kind of process is called wide sense stationary process. Okay, there is another one called narrow nth order joint densities must be same. Here only second order we are considering. If third order, fourth order, fifth order, like that, all orders are stationary joint process, then you call it as a narrow. Nth order stationary are strict sense stationary process. Here it is not like that. Here it is only first order, second order. It is first order and second order. Third order may not be stationary. So in that case, it is called wide sense stationary process. Okay. If up to nth order joint functions are stationary, that means they are not changing, then you can say that nth order stationarity. Okay. If all orders, infinite orders, stationarities, if you consider, then I can call it as strictly stationary. Okay. Strictly stationary means all joint density functions, infinite joint density functions, they are stationary. They are same. Okay. And here it is only wide sense. Wide means wider sense I am thinking. It is not strict sense. Okay. It is not committing too much. The process is not committing too much for us. It is committing on first order average, that is mean, and on second order average, that is nothing but autocorrelation function. Okay. These two only it is committing. That's why we call it as a wide sense stationary random process. Okay. Now I think already I have explained this. For this explanation I have given. So this is this x bar here. In this case, this is x bar. This is also x bar. Like that, all x bars. Then that is first order stationary. And between these two, if I take tau will change. Okay. So for different taus, if I take product of these things and take average vertically, then this is nothing but, so this is general. This is general definition. Correct? This is general definition. This is second order. Okay. This is second order. This is first order. Okay. So first order, second order. Now time averages. So now what I will do is time averages. I will take the waveform here. I will take horizontal. I will take the waveform. Yeah. So here these are taken as small x bar. Take waveform here. Add this waveform. Find the sum. Find the area under the curve. Find the area under the curve. Area under the curve means sum of products. Sorry, it is just sum, simple sum. So it's just integration. Then divided by width of the waveform. Okay, here it is infinite. So if I cannot take infinite, so I have to define some duration. Let us consider that this point is 0, this point is t. So I am taking average. So outside this t I am not considering, before this 0 I am not considering. Between 0 to t, some time slot I have to take. Otherwise, what happens area, because the random signal, time function of a random process is infinite of length, and if I take area under the curve, it may be infinite also. Okay, so we cannot define the infinite energy. So you have to take some time, and what you have to do, you can define the power. So energy in a certain duration within a window time slot, you find the area, then divide it by the time. Okay, so then that's why it is called, random signals are also called as power signals. You can define the power. Okay, but here just mere taking average, I don't call it as a power. I have to square these things, square each value and then take average, then it is called power. Okay, but now at present I am interested in the time average of the waveform, directly x bar. Okay, no squaring, directly just take it. Probably it may be 0 also. Okay, I represent this as small x bar. Capital X bar is used for ensemble average. Small x bar is used for time average horizontally. So this time function has x average, and this time function has x average. This time function has x average. This time function has x average. So all time averages are same. Then I can say that it is a kind of process. I am going to show you. Okay, that I will. There is some name for that. Before that, let me discuss about the these notations, whatever we are using. Okay, so this is what integration minus t to plus t. Probably instead of 0, what I will do, I will put 0 here. I will put 0 here. Minus t. This is minus t. This is plus t. Okay, anything. Then the width becomes 2t. Then the width becomes 2t. Okay. So here minus t to plus t. Minus t to plus t. Here I have the time waveform. Average this. Find the area under the curve. Then you are not taking any modulus value. You should have see that. I am not taking an absolute value. Direct waveform I am taking. Direct time function I am taking. And find the area. This is the area. Area divided by 2 pi. Okay. So area divided by 2t. Sorry, 2t. And what about t? T tends to 0. That means as large as possible you have to take, because your time function spans infinite duration. If you just take small t, then it reflects the local properties. It won't reflect the global properties. So t you should take as much as possible, but definitely you cannot take infinite. Correct? So it is a limiting. Asymptotically, the time should be large. Okay, time should be infinite, but you cannot go for infinite. But that's why we use the limits. The definition in terms of limits we'll use. So the average is taken over all time. The average is taken over all time because sample functions exist for all time. That is infinite, minus infinite, plus infinite. Then mean. So ensemble average. So this is the time function x of t. See, capital X of t is used for ensemble description, small x of t, each waveform. I can say x1 of t, x1 of t, x2 of t, like that I can take horizontally. Okay. So this one I want to average. I am averaging the time waveform. That notation here is A, because E we have allocated for the ensemble average, A we allocate for the time average. So that is what is shown here. So this is the time average of quantity, whatever quantity, it may be voltage or it may be current. Okay, it may be voltage noise or current noise, whatever it may be, it is a random signal. So that's why it is A is used for the time average. Now x bar is the A of x of t, that is what we said. Okay, so this is nothing but this is in general for any function here. This operator we are defining. Inside argument can be anything. Okay, that's why dot means anything. And here specifically we use x of t. Okay, so in this way I have x bar, small x bar here, and similarly I can define rxx. This is rxx, autocorrelation function, time autocorrelation function. It is called time autocorrelation function. And how you are taking this one? X of t plus tau. Okay. So how you are taking this? Here, this is x. So this is what? Okay. Here, see here xn of t, xn. So you take x of t, xn of t. You take this one, for example. Okay. So this one, if I take one value at this point, let us say one value at this point and another value at this point. Same waveform. Okay. So the difference is here tau. Same waveform tau. Now we take one value here, second value, slightly increase the tau like this, or decrease the tau towards minus side, other side. That is also increasing, but in opposite direction. So with respect to t1 here. So you have to fix here tau equal to 0 somewhere. That means t1 equal to t1. This tau equal to 0 means same point, this value multiplied by same point. So, okay. So one value I am taking here, one value I am taking the same form, tau away from that. And these two I am multiplying, again another tau, this is fixed, another tau, another tau. So this is, I can call it as t equal to 0. Okay, t equal to 0 and t equal to something else. Okay, so that is away from 0 tau. So that is nothing but t equal to tau, you can say. So t equal to 0 and t equal to tau. So to both these things you have to multiply. So that is that like that for each tau you have to take. Okay. And for example, this is 1 tau. Okay. Then these two you multiply. Another tau. Take one value here. Same tau, this one. Third one, this value. And here this third value, these two. Because they are separated by tau. First two values are separated by tau. Second two values are separated by tau. Third two values are separated by tau. All are at a time tau. So now you have to take the product of each one. Like that I have infinite products. So you have to take average of that one. So that is what is here the area under the curve here. Basically see here you are multiplying between minus t2 plus t. And basically I should say that it is nothing but in other terms, in simple terms, I can take this waveform. Let us say this is a random waveform. So without shifting. So let us say I have shifted towards this. This is the starting of the waveform t equal to 0. This is t equal to 0. So this shift is tau minus tau this side because it has come forward. So this is what is the common area here? Common area, I mean same waveform. Okay. So this is x of t. This is shifted one. I can say x of t plus tau or t minus tau. Okay, like that. So total waveform I am shifting for given tau or 1 tau. 1 tau I am shifting this and I am finding this area multiplied by this area multiplied by, I mean whatever is there, common area. Let us say because it is infinite. It is infinite. You have to take infinite only. Okay. But because you are limiting to between up to t you are taking. So this is the t I have. After that there is a waveform, but I don't consider. I consider only sometime there is 0 to t. So this is between 0 to t. I will multiply the original waveform. I will multiply the original waveform with the shifted version of the waveform. So this is like a normal autocorrelation function of a random variable or any signal. Okay, we have taken rectangular pulse, we have taken periodic pulse, we have taken linear chirp, we have also taken linear FM. All those things we found the autocorrelation function. So in the same way, you consider this as one waveform and another same waveform shifted. Find the autocorrelation function. I have one autocorrelation function. In the same way, what I will do? Take second waveform, again shift and do for each term. Okay, then take third waveform, again each and get. Okay, so here I will get R XX, probably 1, first waveform, function RXX 2, actually this is a function of tau. Okay, this is a function of tau. This is a function of tau. I am putting here 2 means second waveform. Like that, several autocorrelation functions. So let us say these autocorrelation functions are like this. Okay, something like this. Individual autocorrelation functions are like this. Now you have to take average of all these things. Okay, you have to take average. You take average of all these waveforms, and I mean, okay, so that is what you call as the, I mean, so that is what, okay, so for one random, this here it is given for only one function here, okay, one function between minus t to plus t, and find the area under the product curve, divide by 2t, okay, as large as possible. That is what is time average here. That is nothing but autocorrelation. That means it is equal to one autocorrelation function here. Okay, so that is what is that. Then this operation is equal to one only. This is defined for, so for any one sample function, these two integrals produce two numbers. What it means? Mean value and autocorrelation function. So these two, first order parameter, first order average and second order average. So these two form the time averages. Okay. So x bar and rxx tau. This is small x, rx suffix is small x. That means time wise. Mean value, time average and time autocorrelation function, both are again random variables. So I should say here that this is, for example, I will take here. This is, sorry, not this. Here. This is autocorrelation function. This is autocorrelation function. So this is a random. That means this randoms, this is different shape, this is different shape, this is different shape. Like that I have infinite time functions. I have infinite autocorrelation functions. So these are again random variables. So then what I will do? I will take ensemble. I will add all these things. And if ensemble is, let us say n waveforms, if I take n samples, n functions are, this is also called as n sample functions. Okay, so you are averaging all these things, n copies, random, each has different shape. Okay, then if you average that one, that average is called ensemble average. Okay, so here horizontal average, vertical average. This comes under vertical average. It is nothing but ensemble average. Okay. Now, first I will take, because I have described autocorrelation function first. So this is R small xx here. This is small xx here. This is a set of autocorrelation functions. Set of autocorrelation functions obtained from different sample functions. Okay, each sample function is giving one autocorrelation function, and these are random functions again. They vary. Now you take vertical average, that is nothing but ensemble average, expectation you call it as. This expectation is equal to, this is, what is this one? This is Rxx capital Xx tau. So this is when you find the vertical, you have taken at T1 one variable, T2 one variable, these two you were finding the autocorrelation function earlier. So those functions that is equal to this one. So again you have to vertical you take and find averages. Okay. Then horizontally you do it, find averages. So in one direction if you take, other direction you have to average. So this is, so I should say that the time average is equal to ensemble average. This is the time average. Time average, when I take average over ensemble, it is a constant. Okay. So if the time averages are equal to ensemble averages, I call it as a ergodic random process. So first order ergodic, second order ergodic. First order means only mean is time mean is equal to ensemble mean. Then it is first order ergodic process. Second order ergodic process means time autocorrelation function is equal to ensemble autocorrelation function. Okay. So then in that case, I have this constant. This is also constant function. So these are the two global features of a random process. So whenever you specify a random process, you don't specify by individual member function because it varies randomly. Okay, you cannot predict. If you know one value at current location, current time, at another instant, what is the value? You cannot predict. But when I say it is, the process has same autocorrelation function, same, you can predict the autocorrelation function, you can predict the mean value, but you cannot predict the individual sample functions. Okay. So in other words, time averages equal to the statistical averages. Statistical averages means ensemble averages. Such processes are called ergodic processes. Okay. So I think this is the, so this is all about the mean and autocorrelation functions, because we stop it here because our course is not basically probability theory and stochastic process. It is basically signals and systems. So that's why I given only a brief description about the random process introduction. And because we need autocorrelation function. What do you mean by autocorrelation function of a random signal? What do you mean by mean value of a random signal? So to appreciate those values, I have explained this random process. Now in the next class, probably we will see some simulations. Probably we will see some simulations on this. Then we study about the autocorrelation properties also. Then we pass this random signal. Each random signal is a member of one family. So that family is identified by density functions. Okay, if the density function is Gaussian, you call it as a random process is a Gaussian random process. So that means all sample functions, all variables, vertical variables, random variables, and all sample functions horizontally, they follow the Gaussian density. So that's why the total process becomes Gaussian process. In the same way, if the density functions are uniform, then you call this process as uniform random process. So Gaussian random process, uniform, Poisson's random process. Okay, you have, whatever density functions are available for random variables, because random variables have no time parameter. That is the only difference. If you include the time parameter also, then the total thing becomes the random process. Okay. So thank you very much for your time. I am stopping here.
Like, share and subscribe. Hit the bell icon for more updates.